Welcome. Maybe you have a project called Spectral Energy Distribution. Maybe you're taking a class called Observational Techniques in Astronomy, or maybe you're just a curious soul that likes watching YouTube videos. In either case, if you're given a star, you want to look up a star, you'll probably start in Simbad, in this French University astronomy catalog. And you can search for it in here. This is the name of the star that I'm going to talk about. It's a star in the Small Magellanic Cloud. So once you find your star, you're going to come over here to Vizier, which I guess is some other part of the Simbad domain system, and put in arc seconds about 3, maybe 2, maybe 1, and you should get a plot of your data, kind of like this. And this is your raw data for what you're going to use for your project. There's going to be a few things you'll do with the raw data. You will clip out, prune out the inaccurate data. So you see this one with giant error bars. It's got to go. There's going to be some other things like this one where it says XMM, and that is a survey which is not particularly accurate. XMM is apparently something to do with X-rays, and their photometric data is not up to snuff, even though the error bars on this data point seem to be very small. So you're going to get all this, and you can either download it here, or you can copy and paste it from here. I think they're all the same. And after that, you're going to click on all the data points, and there's a link, depending on what survey or what filter, what system it used. You'll come into the link, and you will get this value for the filter, and this is the flux at 0 magnitude. And you'll need that for all of the data, for all the filters. So you just click on all these, any one of these, and then this Gaia G thing where it turns into a link, you open that up, it goes into here, you'll have to get all these. Then, yeah, there's quite a few. After that, you'll go to your model. So you have your star data, and then this is a model of what stars should do, or do if there's no dust or anything weird around. And you have to find the right one because it varies by temperature and by mass or gravity. So if you happen to have a 4,000 Kelvin star with a log gravity of 0, then this is perfect for you. Otherwise, go to a similar but different website. Use the fluxes. It'll say F in the very last part before the data file, instead of like S or E or something. So get the fluxes, and then you are done with a lot of the internet stuff. Okay, so you have your star's photometric data, and you have your model's stellar flux data. And this is if you copy or paste or download the data from the first one, Simbad, Vizier. You're going to have just lots and lots of stuff. These are the filters that you have to look up those fluxes at 0 magnitude values for. And I would recommend simplifying this. So instead of just after you've copied and pasted, get rid of things you don't need, like tab name. That never comes up, or show all. Those are I think useless, at least for this project. So what your data will end up looking like is much simpler. You'll have your frequency or your wavelength, both. If you want it in multiple units, you can do that. Then you'll have your flux and the error on your flux. Some data points don't have errors on their flux. I got rid of those data points. And it feels weird to say that, since before this project, I feel like all the professors I'd ever had really hammered in keeping data points, even if they're weird or bad or unusual. But this one seems to be quite okay with, oh yeah, it doesn't help you get rid of the data. Like, okay. So all of my data has error fluxes. You'll notice that there's a common values in the wavelengths, because I guess, the camera or something is only sensitive to some certain bands or ranges. But that's going to be important in this data frame, this spreadsheet, because you see all this data that is like 1240 nanometer wavelength. That is, you're going to have to take this entry from the model, which we were looking at, the stellar model with tons and tons and tons of data, and just find it, you know, it's 1240, and then copy and paste it again and again and again and again, so that you have your model lining up with your data in each of these rows. And then hopefully somebody gives you a data file on interstellar reddening, and that is also like your stellar model. Just you're gonna have to find, you know, the values for the wavelengths and then copy paste. Or, you know, if you're Python Pro, you can just like tell it to find the index, and then if the thing equals the other thing, then do stuff. If not, keep going through the iteration loop until you've run over all of your data. But I'm not a Python Pro. So I used this, and then I imported this into Python, which then didn't have to do so much work. And so here, Python, we have my code, and you know, you need to import your libraries, you need to read the data from your file, and these are the variables that I defined in general, and they're going to be used later in the Monte Carlo approach. Here's a flux units, pick your units, you can do Jansky, SI, whatever, just none of them are the same, so you have to switch all of them, except one, into one. And then here's all the data. Here is the data under short wavelengths. And so you're going to be fitting your photometric data to your stellar model. And you're also going to be de-reddening your photometric data. And you only want to have it fit based on the short wavelength, high energy data, because the low wavelength, low energy, high wavelength data is picking up two entirely different phenomena, and so they should not match. The photometric data from Vizier has dust around it, and so it's going to have this really high excess. The stellar model from the website, the Italian Astronomical Observatory website, does not have dust, and so it decays down to zero quickly. You do not compare those two parts. You only compare the early parts, which is short wavelength, high energy data, and those should match because the dust doesn't influence that range of wavelengths, at least not significantly. And then you're going to make a for loop to optimize your EV minus B, or reddening. And it's weird in that they give you your fluxes in Jansky from Vizier, and then your interstellar reddening is in magnitudes, and hopefully this formula works. That my final answer was off by like a factor of 10 to the 6, so I might be doing something wrong here. And change the magnitude, and then I went back from magnitudes to fluxes, and then so that de-reddens your data. Then you need to shrink your model, because your model's being like integrated over an entire steradian, which is like, I don't know, a sixth of the sky, and obviously your telescope here on Earth doesn't cover a sixth of the sky of the perspective of a star in a small Magellanic Cloud. And so you need to normalize that, or scale it, and to normalize it, you're just going to find a data point somewhere in the valid range, so 500, 700, 800 nanometers, maybe 200 nanometers, and 100 nanometers, divide it, or make the ratio between the flux and your de-reddened data point. And then you're going to multiply the entire model by that tiny, tiny, tiny number, or divide by that very large number. And so you get, instead of this big model, 10 to the 8, whatever, in SI units, you shrink it down to something that's like Jansky's. And it's close to all of your data, and it's exactly your data at one point. Pick a point in like the I band or J band or something, or ask the teacher. Then you're going to calculate chi-squared. Hopefully you are familiar with NumPy. If not, YouTube NumPy and somebody will give you a tutorial. And then, yeah, you find the chi-squared for all values, find the minimum chi-squared, and locate where that minimum is, and then get the reddening, or EV minus V, at that minimum. Then you can plot it. This is a plot of it. And then you compare not just the short wavelength data, but rather all of the data with the one best reddening, EV minus B, that is applied to the short wavelength data. And you can plot that, and then you're kind of done with the first part. Luminosity, I did some expansion or conversion over this local area of the telescope and just tried to figure out how big the sphere around my Small Magellanic Cloud star was, and then, yeah, factored the difference in area between that giant two-dimensional plane that is a sphere, which one tiny percent of is covered by my telescope. But I got the answer quite wrong, so hopefully you can find a better way. And then you'll find the temperature. Temperature is a black body radiation, so there's Planck's law and there's Wien's displacement law. You can try to use both or either or something. And then you do a Monte Carlo, and hopefully you'll have this random thing work out for you. And the instructions were to use 0.05, and I kept getting numbers that were way too small. So I started just playing with 0.05, and I ended up getting the correct answer at 0.2. And the correct answer is, in essence, when the average Monte Carlo value is equal to your reddening. So you want those two to line up. And those two are going to line up at some point, however it is and whatever. And then when they line up, because it's a Monte Carlo simulation, there's going to be randomness, there's going to be differences between all the data points and the average, and the standard deviation of that distribution is supposed to be your error on your reddening. So I got a reddening of 0.15, and then I did this Monte Carlo analysis, and I changed the scale thing so that it was 0.2, and when that happened, I got an average reddening from the Monte Carlo analysis as 0.15. They matched, and then that meant that the error was the standard deviation, and it was something like 0.025, and so that was the range of my reddening or something. And that was the end of the code, at least of the code that I used. These are all the efforts that I made before getting as far as I got before the deadline. Hopefully you're a Python pro. If you're not, you should be by the end of it. What's next? Okay, so maybe you have a report. Maybe you're in Belgium and you like tables of contents, and you write abstracts, and you identify stars, and you take some pictures from Vizier. This is 10 arc seconds, so you're getting tons of data, and then this is the better 3 arc seconds, so you get pretty clean data. And then this is from Python, and I managed to make sure that my data looked like the Vizier data. And then this is the model, the stellar model. tons and tons and tons of data points and huge values, like 10 to the 6, 10 to the 8 or something. So you have to scale it down to fit your data, otherwise you'll just get a hump and a very small flat line underneath it. Words, words, words. Hopefully you like typing. Chi-squared. There's your formula for chi-squared. And so when you're iterating over your EB minus V or reddening values, you can, what in essence is happening is you're getting this shift around a middle. Whatever middle point you define, if it's this one here, then it's going to be accurate here. But this over on the left and this over on the right are going to shift. You see this one moves up, all these move up, and then these move down, and these move down. And so of these three pictures, this one is the best. But if I kept drawing more pictures above this one, eventually the blue lines will go underneath and lower, 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 and they get inaccurate. So there's some sort of optimization. Obviously, the larger it gets, the way more inaccurate it gets. And that's where my 0.15 came in. Okay, so here's your chi-squared for all your reddenings. It looks monotonic, but it's not. And you'll see that in the next graph. Yeah, so there's a minimum. You just put it on a log axis, or you zoom in really far to this early part, and you'll find the minimum. And that's where your data is reddened optimally to match your scaled model. And there's your data and your scaled model at that optimal reddening. And you can see, it's still kind of bad here and very bad here, but that is supposed to be, because this is the infrared excess caused by the dust, circumstellar dust, surrounding your Small Magellanic Cloud star. And this model here does not have the dust, it's just pure star, and so they should diverge. But in the beginning, they should be very similar. And yeah, make your stuff math pretty nice, neat labels. Okay, so here's the Monte Carlo. This was what I got from doing it correctly, but I must not have been, because this average is about 0.009, and that is way too small. It's supposed to be 0.15, the same as the reddening. And so I started fiddling with the scale value in this NumPy command. And if I got a scale value of 0.2, then this scatter was neatly right around 0.15, yeah. And that is where I wanted, that was my average, or this average is equal to the reddening of my best photometric data. And then the standard distribution around this average was something like 0.025, and so that suggests that my error on my reddening from the earlier part is also about 0.025. Maybe you like tables. And for the dust, there was Planck's law and Wien's displacement law. And if you do something silly, you can get, I don't know, temperature estimates for both or something. And I imagine I did part of that wrong. I think that K should have been capitalized in temperature. Oof. You can make a discussion, you talk about error, and nothing's ever correct, and what you would do in the future. And then you conclude it, but I wouldn't even bother with a conclusion. Have your references and appendices. So here's again reddening, where you have, pretty close and then really far, and then you're lowering this stuff on the left and raising this stuff on the right. And that is going to, if you do it over all the data like this, then you're totally messing up, because you're not trying to get this data down here to match this data down here. This high wavelength blue data is picking up dust. This high wavelength yellow data, orange data, is picking up nothing. And so they're supposed to diverge. Therefore, only use the left-hand side's data points. Remember Vizier where you got the data? Yeah, that's there. Okay. And if you want, you can copy and paste your Python code into your report. There's a neat command in Overleaf called, or screenshot it, Neat command I believe called verbatim, but you have to like use a package for it or something, and then you don't have to fiddle with any of the format. Best of luck to you.